In 1981, 4 astronomers stared into a terrifying silence, while Robert Kirshner and his colleagues expected to map a complex cosmic web. The data revealed a region so vast that light seemed to lose all purpose. This expanse stretched across 330 million light-years of absolute nothingness. To cross this chasm at light speed would take longer than the entire history of the mammalian species. If the Milky Way resided in the center of the Boots void, humanity would not have known other galaxies existed until the 1960s. The night sky would have appeared as a featureless black shroud. This desert defied every expectation. This discovery marked the first reckoning with the Great Nothing. The Boots void serves as a symptom of a much deeper truth governing the entire cosmos. While humans focus on the bright islands of stars, these structures represent the exceptions. The true architect of the universe remains invisible to our eyes. Emptiness dictates the evolution of reality. 95% of the volume of the universe consists of these cosmic voids. Reality functions as a sponge of holes, where the vacuum dictates physics and matter exists only as a byproduct squeezed into the corners. These galaxies we call home represent the cosmic sediment gathered in the forgotten corners of reality. In this perspective, the entire history of human civilization resembles a mold colony growing on the back of a cosmic refrigerator. Understanding the universe requires a fundamental shift in perspective. We must stop looking at the stars and start examining the spaces between them. From the perspective of the universe, we represent the anomaly, and the vacuum serves as the standard. This investigation descends into the depths of the cosmic vacuum to uncover why nothingness functions as the most powerful laboratory in existence. Mainstream science often treats space as a passive stage, but the evidence reveals that these voids drive cosmic evolution. Our journey connects the earliest fluctuations of the Big Bang to the modern foam-like structure of the cosmos. We will examine how the void preserves the memory of the primordial universe far better than any cluster of galaxies. Voids remain linear and pristine, while high-density regions lose the history of the early cosmos through violent galaxy formation. The official story of the universe focuses on light, but the complete truth remains written in the dark. We will reveal how the absence of matter allows the dark sector to unveil hidden secrets of the vacuum. Over the course of this journey, we will trace the hierarchy of emptiness from the smallest pockets of vacuum to the supervoids that dictate the fate of reality. Our investigation begins with the universal blueprint defining every void, regardless of scale. We will then descend into the dark laboratory, where the expansion of the vacuum reveals the nature of dark energy and the hidden laws of modified gravity. Modified gravity represents a theory suggesting that our current understanding of the force remains incomplete, proposing that gravity changes behavior in the vast reaches of the vacuum. Beyond the laboratory, we will witness the violent sociology of the cosmic web, where larger voids merge and smaller spaces perish under the weight of collapsing clouds. This process, known as the void-in-cloud effect, demonstrates how the environment dictates the survival of the vacuum. We will explore the Alcock-Pasinski test, a method using the spherical nature of voids to measure the expansion of space. Finally, we confront the fingerprints of ghost particles and the inevitable future where the walls of our cosmic cage collapse under the relentless pressure of dark energy. The question remains not how matter formed in the universe. The question focuses on why nothingness dominates the structure of all known reality. Emptiness represents the ultimate architect of the cosmic web. By the end of our investigation, we will understand that we do not stand as the masters of the cosmos. We reside merely as the inhabitants of the walls, watching the vacuum decide our fate. This transition begins now. Here is the deal. If you think there is value in taking the time to really understand something deeply, that is what we do here. So, if you want more of this, hit subscribe. Let us figure this out together. That transition found the first physical footprint in 1981. Our reckoning with the heart of the cosmic vacuum centers on that year. In that era, the scientific community operated under the assumption that the universe functioned as a relatively smooth distribution of matter, occasionally punctuated by the brilliant clusters of galaxies. When the first comprehensive redshift surveys began at the Kitt Peak National Observatory, the intention was to confirm this vision of a crowded cosmos. These astronomers represented a new generation of cosmic cartographers, researchers who sought to map the grand architecture of reality with a precision never before attempted. They spent hundreds of hours in the cold mountain air of Arizona, watching the faint photons of distant worlds strike the mirrors of the telescopes. The process remained grueling and slow. In the early 1980s, the technology required to measure the distance of thousands of galaxies remained in a primitive state. Every data point required a patient gathering of light, a careful measurement of the spectral lines that revealed the velocity of an object moving through the expanding dark. The team employed a technique called redshift mapping to build a three-dimensional model of the sky. They expected to see a messy but full mosaic of islands, a continuous web of matter stretching across the horizon. They anticipated finding a universe that was busy, a place where the light of galaxies filled the void, like the lights of a distant city seen from a mountaintop. But as the numbers began to emerge from the computers, the team realized that the city was a ghost town. What the researchers found instead was a gap in the heavens, so profound that the results challenged the very foundation of cosmology. The team discovered the Boots Void, an expanse of nothingness stretching across 330 million light-years. The initial data appeared so empty that the team initially suspected equipment failure. But as the survey continued, the silence became undeniable. The team was staring into the largest hole in existence. Such emptiness was uncovered using measurements of the Doppler effect. This absence of light was more than an anomaly. The discovery offered a terrifying demonstration of how much of the universe remained hidden from our island-based perspective. When a galaxy moves away from the observer, the light of the galaxy stretches toward the red end of the spectrum. By measuring this redshift, astronomers could determine the velocity and the distance of the objects in the survey. The team pointed the instruments toward the constellation of Boots, a region of the sky known as the Hertzman. The researchers expected to see a steady stream of galaxies appearing at various distances, a predictable layering of matter as the team looked deeper into the past. Instead, the astronomers hit a wall of silence. For a range of redshifts, corresponding to a distance of hundreds of millions of light-years, the data showed almost nothing. The survey revealed a spherical hole in the universe. To visualize the scale of this structure, consider the size of the Milky Way galaxy. The Milky Way measures approximately 100,000 light-years across. The Boots Void is so large that the region could contain 10,000 Milky Way galaxies. This scale is difficult for the human mind to process. If an observer were to travel across this void at the speed of light, that observer would move for 330 million years without passing a single significant cluster of stars. The density of matter in this region is less than 1/10 of the average density of the universe. In a typical volume of space this large, astronomers expect to find at least 2,000 galaxies. The survey found fewer than 60. These few, isolated galaxies are like lost travelers in a desert, separated by distances so vast that the objects can never hope to interact. This low density represents a concentration of matter so low that the particles of gas and dust inside the void rarely collide. The vacuum has won. The existence of the Boots void created a crisis for the standard model of the cosmos. This problem is known as the nothingness paradox. To understand the tension, we must look back to the earliest light in the universe, the cosmic microwave background. This radiation represents the afterglow of the Big Bang, a snapshot of the universe when reality was only 380,000 years old. The data from the cosmic microwave background shows a universe that was almost perfectly smooth. The fluctuations in density were tiny, measuring only 1 part in 100,000. Gravity is a slow architect. For gravity to take those tiny fluctuations and dig a hole 330 million light-years wide, the process requires an immense amount of time. According to our current understanding of physics, 13.8 billion years is not enough time to create a structure as empty as the Boots void. This tension arises from the fundamental way matter moves. In the standard model, the growth of cosmic structure is a linear process for most of cosmic history. Matter falls into overdense regions at a predictable rate, while underdense regions empty out with a corresponding speed. The cosmic microwave background reveals that the original density fluctuations were extremely small, barely ripples in the primordial soup. For these ripples to expand into a hole 330 million light-years across, gravity must overcome the expansion of the universe itself. This process is like trying to dig a trench while the ground is being stretched apart by a massive machine. If gravity is the only force at work, the trench cannot grow faster than the machine stretches the ground. The presence of the Boots void suggests that either the trench was dug much earlier than science believes, or the machine is working differently in the dark. Astronomers call this the void in cloud problem. If the surrounding matter is dense enough, the gravity of the wall actually pulls matter out of the center, accelerating the growth of the emptiness beyond the speed of standard expansion. This mystery leads us to the Sachs-Wolf effect. This effect describes how the photons of the cosmic microwave background gain or lose energy as the photons pass through gravitational wells and hills. When light passes through a massive void, the light should experience a gravitational redshift that leaves a specific signature on the sky. But the signatures science observes do not match the voids we see. This discrepancy implies that the vacuum possesses an intrinsic energy that we are only beginning to understand. Dr. Richard Sachs and Dr. Arthur Wolf first proposed this mechanism in 1967, long before the Boots void was ever mapped. The researchers realized that the large-scale structure of the universe acts as a series of obstacles for the ancient photons. When a photon enters a gravitational well, the light gains energy and shifts toward the blue. When the photon leaves, the light loses energy. If the universe expands during the journey of the photon, the energy loss is not perfectly balanced. The void becomes a hill that the light must climb. This process leaves a cold spot in the cosmic microwave background, a fingerprint of the emptiness that existed billions of years ago. The problem arises because the Boots void is too empty and too large for the expected signal. We are forced to ask if the vacuum possesses a form of negative pressure that actively pushes matter away. If this pressure exists, the voids represent more than empty spaces. The regions function as the most powerful repulsive engines in the universe. Perhaps the vacuum itself possesses a strength we have not yet measured. This mystery forces us to reconsider the role of the void. We have long treated space as the empty stage where the drama of matter unfolds, but the nothingness paradox suggests that the stage is the main character. The vacuum is not a passive gap. The vacuum is an active force, a cosmic engine that carved the heavens into the shape we see today. To understand the magnitude of this discovery, imagine the universe as a vast, dark ocean. For centuries, humans have resided on small, crowded islands, believing that the ocean floor is covered in land, just like the ground beneath our feet. We look out from our shores and see other islands in the distance, and we assume the entire world is a collection of these solid places. We think the water between the islands is just a temporary gap, a minor distance to be crossed. But the discovery of the Boots Void reveals that the islands are the exception. The ocean is not a gap between lands, rather, the water represents the world. These islands are merely the sediment that has gathered in the rare places where the currents allowed the matter to settle. This realization challenges the Copernican principle, the idea that humans do not occupy a special or privileged place in the universe. Since the time of Nicolaus Copernicus, we have learned that the Earth is not the center of the solar system. We have learned that the Sun is not the center of the galaxy. We have even learned that the Milky Way is not the center of the universe. But we still maintain a form of biological bias. We believe that matter is the center of reality. We think that because we are made of atoms, the universe must be made of atoms. But the voids tell a different story. We reside in a high-density impurity, a cosmic mistake where matter has managed to cluster together. We are like barnacles growing on the hull of a ship, believing that the world is made of steel, unaware of the vast, deep blue that surrounds us. Positioned at the center of this silence, the Milky Way would exist as a lonely island in a dark ocean. The light from distant clusters would be so red-shifted and faint that our telescopes would perceive only a featureless void. This isolation would define our entire understanding of physics, leading us to believe that our single galaxy constituted the entirety of reality. We would look out into the darkness and find a universe of pure, unadulterated nothingness. The mystery of the Boots Void remains one of the greatest challenges to the standard model of cosmology. In the lambda cold dark matter model, structure grows from small fluctuations in the early universe. Gravity pulls matter together to form galaxies and clusters, while the spaces between these objects naturally empty out. However, the size of the Boots Void is difficult to explain through standard gravitational growth alone. Computer simulations of the early universe can produce small voids with ease, but the formation of a supervoid this large requires a set of initial conditions that are exceptionally rare. Some researchers suggest that the Boots Void formed through the merger of multiple smaller voids, a process known as the hierarchy of emptiness. In this view, smaller bubbles of vacuum expanded until the regions touched, eventually collapsing the walls between them to create a single massive expanse of nothingness. This growth implies that the void represents more than a whole, but a dynamic, growing entity. The boundary of the void acts as a pressure front, pushing galaxies outward and concentrating matter into the surrounding filaments. This process creates the cosmic web we see today, but this growth also means that the voids are the primary drivers of structure. The regions are the engines of expansion, pushing the islands of light into the corners of reality. This discovery marked a fundamental shift in the epistemic stance of astronomy. We can no longer treat the vacuum as a passive background. From the perspective of the universe, the stars are the anomaly. The empty space is the standard. We spend our time studying the 5% of the universe that is made of visible matter, while ignoring the 95% that consists of the vacuum and the dark sector. This observational bias is a consequence of our environment. We are attracted to the light because we are made of light, but the truth of the cosmos is written in the silence. The Boots Void serves as a reminder that the universe does not belong to us. This cosmos remains far from a place built for life or for stars. Reality serves as a vast expanding desert of nothingness, where we exist merely as the thin film of dust on an abandoned library shelf. If we wish to understand the architect of reality, we must look into the dark. We must examine the gaps. The paradox of the universe is that the most significant structures are the ones that contain the least amount of matter. The paradox of our existence begins with the expectation of a matter-filled universe. Since the era of Isaac Newton and Albert Einstein, our equations have focused on the behavior of massive objects. We defined gravity by how gravity pulls matter together. We defined light by how light interacts with atoms. This technical focus created a narrative where the universe is a collection of objects. We imagine the cosmos as a dense field of stars and planets, a busy and crowded place. But the reality is that the universe is staggeringly empty. If we take the total mass of the universe and spread this mass evenly across the total volume, the density is less than 6 protons per cubic meter. For comparison, the air we breathe contains 10 to the power of 25 molecules per cubic meter. The universe is a vacuum that happens to contain a few scattered impurities. The reason humans perceive the universe as crowded is only because we reside within one of those impurities. We are like travelers on a cruise ship who believe the world is made of metal and carpet, forgetting that the ship is a tiny speck on a vast and indifferent ocean. This perspective bias masks the true influence of the dark sector on cosmic structure. This bias is so deeply ingrained that we have spent billions of dollars and millions of hours cataloging the lights while the shadows remained unmapped. We have mapped the continents but ignored the oceans. We have counted the trees but failed to see the forest. This matter-based myopia has limited our understanding of the forces that truly shape the heavens. We look at a spider web and admire the silk, forgetting that the web is mostly air. The air provides the volume, while the atmosphere provides the space. This silk only exists to define the boundaries of the nothingness. To visualize the structure of the cosmic web, imagine a giant sponge. The sponge material represents the distribution of matter. The holes in the sponge are the cosmic voids. In a standard sponge, we focus on the material that makes up the structure. We think of the holes as a lack of sponge, but in the universe, the holes are the dominant feature. 95% of the volume is occupied by these holes. The material of the sponge, the galaxies and clusters, exists only because the holes are expanding and pushing the material into thin walls and filaments. The expansion of the voids is like a bathtub being filled with water. As the water level rises, the liquid pushes all material into the corners. If you place a few drops of food coloring in the water, the color spreads out until the pigment is barely visible. But if you have objects floating on the surface, the floating items are pushed together as the water moves. The voids represent the water, while the galaxies function as the floating objects. Movement of the universe is not driven by the galaxies pulling each other. Instead, the acceleration arises from the vacuum expanding and forcing the matter to move. One problem with our current understanding is that we rely on biased tracers to map the universe. We use galaxies as markers for where the matter is located, but galaxies only form in high-density regions where the gas is cold enough and dense enough to collapse. This tracer bias means that our maps of the universe are like maps of a city at night where we can only see the streetlights. We see the bright spots, and we assume the city is a collection of lamps. We miss the streets, the buildings, and the vast spaces between the lights. This tracer bias makes the voids appear even emptier than the regions actually are. In reality, the voids may contain dark matter and diffuse gas that do not emit light. Detecting this hidden mass is one of the greatest challenges of modern astronomy. We must use gravitational lensing to see the invisible structure of the vacuum. Gravitational lensing occurs when the mass of an object bends the light from a more distant source. By measuring how the light from distant galaxies is distorted as the light passes through a void, we can map the true distribution of mass. This technique reveals that the voids are more than empty holes. They are regions where the dark matter density is low, but not zero. The existential weight of this realization is that we exist in the places where matter has been squeezed together by the expansion of the dark sector. From the perspective of the vacuum, the history of the Milky Way is a minor event. The formation of the Sun and the Earth represents a tiny fluctuation in a universe that is otherwise dedicated to the expansion of nothingness. Our significance is not found in our mass or our location. The weight of existence is found in our ability to see the ocean while standing on the shore. We are the consciousness of the wall dwellers, looking out into the void and realizing that the hallway is the home. The paradox of the nothingness is that emptiness is the most important element in existence. We are the exceptions that prove the rule. We are the dust that has settled in the corners of a cosmic palace, and our task is to understand the architecture of the rooms we can never enter. This recognition is the first step toward a true cosmology, a science that acknowledges the vacuum as the primary architect of the cosmic web. The stakes of our investigation are defined by the choice to look into the dark. If we ignore the voids, we ignore the majority of the physical volume of the cosmos. We ignore the engine that drives the acceleration of the universe. The history of structure formation theory has long been dominated by the study of peaks. We have spent decades building models of how galaxies form and how clusters merge. We have become experts in the high-density regions of the universe. But these regions are messy. When galaxies form, the clusters heat the surrounding gas, the stars explode in supernovas, the matter falls into black holes. These processes create a form of cosmic noise that erases the memory of the initial conditions of the universe. The high-density regions are like a crowded city square where thousands of people have walked across the ground, erasing the footprints of the first person who arrived. To find the true history of the cosmos, we must look for a place where no one has walked. We must look at the voids. They are the only regions where the original signals of the early universe remain undisturbed by the violent processes of baryonic physics. They are the restricted archives of the cosmos, preserved in a state of eternal silence. When we ignore the voids, we do more than ignore the background of the cosmos. We ignore the very engine of reality. We ignore the dominant volume of existence. To understand the universe, we must descend into the dark. We must look at the nothing. The blueprint of the vacuum awaits our examination. This investigation into the cosmic void is more than a study of holes in space. Such a narrative reveals how nothingness became the master of the universe. Our story is a journey into the heart of the forces that decide the fate of existence. The nothingness is more than an absence. Nothingness represents the architect, and the time has come to study the design. Fulfilling this mission is the task before us. Our journey now moves from the discovery and the paradox into the mechanical blueprint that defines every empty space in the heavens. This shift begins with the realization that every void follows the same cosmic code. To bridge this gap, we must examine the Hamaus Wandelt profile, a universal mathematical signature that describes the density of every void, regardless of scale or age. This profile represents the fundamental blueprint of emptiness, revealing how gravity and expansion negotiate the boundaries of the vacuum. This pristine record is how the void remembers. The transition into the blueprint of the vacuum begins now. In 2014, a team of researchers including Nico Hamaus, Paul Sutter, and Benjamin Wandelt published a series of findings that fundamentally altered the perception of the cosmic vacuum. Before this work, astronomers viewed cosmic voids as irregular, chaotic holes with little internal structure. The consensus suggested that every empty space was a unique accident of gravity, a messy byproduct of the matter clustering elsewhere. However, the Hamaus team used data from massive sky surveys and sophisticated computer simulations to prove that every void, regardless of the size or age of the region, follows a nearly identical mathematical blueprint. This discovery took place during a period of intense development in computational cosmology, as the Sloan Digital Sky Survey provided the first high-resolution maps of the large-scale structure of the universe. At the University of Illinois and the Institut d'Astrophysique de Paris, these scientists began to look for patterns in the nothingness. Such researchers realized that the voids existed as more than gaps between the galaxies. These structures functioned as physical objects with a predictable and universal internal architecture. This realization marked a turning point. Every result meant that the emptiness possessed a code, a set of rules that governed the distribution of mass from the center of the vacuum to the edge of the surrounding walls. Findings demonstrated that the density profile of a void is self-similar, meaning a small pocket of vacuum in a local filament looks remarkably like a supervoid stretching across hundreds of millions of light years. This discovery brought a sense of order to the desert of the heavens. The specific structure identified by the researchers is known as the Hamaus-Sutter-Wandelt profile. This profile describes the density of matter as a function of the distance from the center of the void. At the very center, the density reaches the lowest point, often reaching values of less than 10% of the cosmic average. As the observer moves outward from the center, the density remains low and relatively flat for a large portion of the radius. The region represents the core of the vacuum, a place where the expansion of space has cleared away almost all baryonic and dark matter. However, as the observer reaches the boundary of the void, the matter begins to rise sharply. The rise does not stop at the average density of the universe. Instead, the mass piles up into a massive, overdense ridge known as the compensation wall. This boundary consists of the galaxies and dark matter that have been pushed out of the void by the internal pressure of the vacuum expansion. Gravitational pressure from the surrounding wall acts as a barrier, defining the physical limits of the empty space. The Hamaus-Sutter-Wandelt profile uses a specific set of parameters to describe the shape of the void, accounting for the steepness of the interior slope and the height of the exterior ridge. Such a mathematical model matches the observed data with incredible precision across a wide range of scales. Whether the void is 10 million light-years wide or 100 million light-years wide, the ratio of the central emptiness to the height of the surrounding wall follows the same logic. Such consistency represents a hallmark of a fundamental physical process. This profile reveals that gravity and dark energy negotiate the boundaries of the vacuum in a way that is identical across the entire history of the cosmos. Such stability makes the density profile a powerful tool for measuring the evolution of the universe. To understand the mechanics of the universal density profile, imagine the universe as a vast field covered in a deep, fresh layer of snow. The snow represents the average density of matter. Now, imagine a series of children scattered across the field, each trying to build a snow fort by shoveling the snow outward from a central point. As each child clears a circle, the ground in the center becomes bare, representing the core of the cosmic void. The snow that was once in the center does not disappear. Instead, the child piles the snow into a circular wall at the edge of the cleared space. This mound of snow is the compensation wall. If the observer looks at the field from above, the view reveals a series of dark circles surrounded by white ridges. Now, consider the size of the circles. Some children are small and only clear a space the size of a hula hoop. Other children are older and clear a space the size of a parking lot. Despite the difference in scale, the shape of the result is identical. Every circle has a bare patch in the middle and a high ridge at the edge. Such a ratio of the depth of the hole to the height of the wall remains consistent because the snow moved from the center must occupy the boundary. In the universe, gravity is the child with the shovel. This force pushes the matter out of the underdense regions and piles the matter into the filaments and walls of the cosmic web. The universal density profile is the blueprint that tells the observer exactly how high that wall will be and how deep that hole will go. Every analogy demonstrates that the voids represent active constructions shaped by the movement of the mass that used to fill the space. The mystery of the universal density profile arises when the observer looks at the very largest supervoids. While most voids follow the Hamaus-Sutter-Wandelt profile perfectly, the largest structures in the universe exhibit unexpected behavior at the center. In some observations, the density at the core of a supervoid appears lower than the theoretical minimum allowed by the standard model of gravity. The discrepancy suggests that an external force beyond simple gravitational expansion is driving the evacuation of the vacuum. Some researchers argue that the evidence points to a fifth force of nature, a modified form of gravity that becomes stronger in the absence of matter. The theory proposes that in high-density regions like the solar system, the extra force is screened or hidden by the presence of mass. But in the pristine isolation of a supervoid, the force is unscreened, providing an extra push that clears the center of the vacuum with an efficiency that standard physics cannot explain. Another possibility suggests that the mass of neutrinos plays a role in shaping the core of the void. Neutrinos are nearly massless particles that travel at close to the speed of light. Because the particles move so fast, the neutrinos can escape the gravitational pull of the surrounding walls and settle in the center of the vacuum, subtly altering the density profile. The challenge for astronomers is to distinguish between the two possibilities. Is the anomaly in the profile a sign of new laws of physics? Or is the profile the fingerprint of the most elusive particles in the universe? The answer remains hidden in the statistical noise of current surveys. The existence of a universal blueprint for emptiness is a profound reminder of the mathematical indifference of the universe. Scientists often search for meaning in the unique and the complex, believing that the diversity of the cosmos is a sign of a creative or chaotic process. But the universal density profile tells a different story. This profile reveals that the vast majority of the volume of reality follows a rigid and predictable code. The emptiness is not a place of freedom or randomness. The vacuum represents a place of absolute conformity. Every supervoid is a mirror of every other supervoid, repeating the same architecture across trillions of light years. The consistency implies that the vacuum represents the fundamental state of the universe, a baseline of reality that remains unchanged while the matter and the light struggle to survive in the corners. The walls represent the messy and overdense ridges where the universal profile reaches a peak. Galaxies are the byproduct of the vacuum following the blueprint. Human history represents a footnote to the expansion of a whole that was always meant to take that shape. The blueprint was written at the beginning of time, and the universe has spent 13.8 billion years executing the design with cold and perfect precision. The concept of linear memory in cosmic voids emerged as a solution to one of the most frustrating problems in modern cosmology: the erasure of the history of the early universe. For decades, astronomers have tried to use the distribution of galaxies to reconstruct the initial conditions of the Big Bang. However, high-density regions are chaotic and violent. When matter collapses to form a cluster of galaxies, the process is non-linear, meaning the small initial fluctuations are twisted, folded, and merged until the original signal is lost. This erasure is like trying to determine the shape of a single snowflake after the snowflake has been incorporated into a massive, rolling snowball. The physical details are ground away by the force of the movement. In the 1990s and early 2000s, researchers realized that the underdense regions of the universe might provide a different path. Because the voids expand rather than collapse, the matter inside the regions moves in a much simpler and more predictable way. The initial conditions are not crushed, the conditions are simply stretched. The realization led to the development of void-based cosmology, a field that treats the vacuum as a pristine archive. Scientists like Ravi Sheth and Rian van der Wegert were instrumental in formalizing the idea that the voids preserve the linear memory of the primordial cosmos, offering a clear window into the first moments of time that the galaxies have long since obscured. The reason voids possess linear memory is found in the physics of Lagrangian dynamics. In high-density regions, matter experiences what is known as shell crossing. As gravity pulls particles toward a center of mass, the trajectories of the particles eventually cross one another, leading to a complex and turbulent state of motion. This shell crossing represents the moment when the memory of the initial state is destroyed. The movement becomes non-linear and chaotic. However, in the interior of a cosmic void, the density is so low that the particles of dark matter and gas move away from one another. Because the paths almost never cross, the flow of matter remains smooth and laminar. Absence of crossing means the current position and velocity of a particle in a void can be traced back to the starting point with a simple linear equation. Such expansion of the void acts like a magnifying glass, taking the tiny fluctuations from the early universe and enlarging the signals without distorting the underlying pattern. The process is known as linear evolution. While the galaxies have undergone billions of years of mergers, star formation, and supernova explosions, the voids have grown larger. Observed today, the universal density profile is a direct scaled-up version of the density fluctuations that existed when the universe was only a few seconds old. Such preservation allows cosmologists to measure the power spectrum of the early universe with a clarity that is impossible in the crowded environment of a galaxy cluster. Vacuum represents a place of preservation, not change. To grasp the concept of linear memory, imagine two different ways of preserving a drawing on a piece of rubber. In the first case, the observer takes the rubber and crumples the material into a tight, hard ball. The observer squeezes the rubber with all strength, folding the surface over the rubber thousands of times. If the observer then tries to look at the drawing, the view reveals only a messy tangle of lines and colors. The original image is gone, destroyed by the non-linear process of compression. The crumpling represents what happens to the history of the universe in a cluster of galaxies. Gravity crumples the primordial signal until the signal remains unreadable. In the second case, the observer takes an identical piece of rubber with the same drawing, and the observer stretches the material in all directions. As the rubber expands, the drawing grows larger. The lines get thinner and the colors get lighter, but the shape of the drawing remains perfectly intact. Every detail remains visible, just on a larger scale. Such stretching represents what happens in a cosmic void. Cosmic expansion stretches the primordial signal, but the signal is never crumpled or folded. This linear memory represents the fact that the drawing remains preserved by the simple act of growing larger. Vacuum functions as the stretched rubber of the cosmos, holding the original map of the Big Bang in a state of perfect, expanded clarity. This preservation allows astronomers to look at a void today and see the exact shape of the universe at the dawn of time. Linear memory hides a mystery in the detection of the very first stars and black holes. If the voids are truly pristine archives, the regions should contain the chemical and gravitational signatures of the earliest objects in the universe. Some theories suggest that the first generation of stars, known as population 3 stars, may have formed in the low-density environments of the early voids. Primordial stars were made entirely of hydrogen and helium, and the stars would have been much larger and brighter than the stars seen today. If the stars existed, the light would have left a specific ionization signature on the gas inside the void. However, current observations have yet to find a definitive sign of the primordial objects. The lack of discovery creates a tension. If the memory of the void is perfect, why can astronomers not see the first signatures written in the vacuum? Some researchers believe that the signal exists, but the signal is masked by the light of much closer and more modern galaxies. Others suggest that the voids are even emptier than scientists believe, and that the first stars only formed in the dense filaments. This situation leaves a haunting question. Is the void a perfect record of every event, or does the void represent a record of a universe that was much more empty and silent than our models predict? The lack of data is itself a form of evidence, pointing toward a primordial past that remains stubbornly out of reach. The linear memory of the vacuum suggests that the universe has a way of remembering the past, but only in the places where nothing happens. Humans believe that activity defines importance, but the cosmos reveals that activity is the enemy of memory. The more action that occurs in a region of space, the more the past is erased. The stars and planets represent the noise that drowns out the original signal of creation. Only in the absolute silence of the void can the truth of the beginning survive. The silence implies that the most significant parts of human history may not be the wars fought or the cities built, but the quiet moments that left no trace. From the perspective of the universe, the void is the only place where the story of the Big Bang is still being told. We reside in a region of profound amnesia, a crowded and violent wall where the past has been ground into dust. The memory of the universe is held in the places where humans are absent. Mapping the emptiness of the universe required a new set of mathematical tools, leading to the adaptation of a technique from the field of digital image processing, known as the watershed transform. In the late 20th century, cosmologists realized that simply counting galaxies was not enough to define the boundaries of the cosmic voids. Galaxies are discrete points, but the voids are continuous volumes. To map the regions, researchers needed a way to segment the universe into distinct regions of underdensity. In 1996, a group of astronomers, including Mark Nerink and Vicente Martinez, began to apply the watershed transform to cosmic maps. The technique was originally developed for computer vision to help machines identify objects in a cluttered image by looking for the edges and the basins. By treating the density of the universe like a topographic map, the team mapped the catchment basins of the cosmos. The work turned the study of emptiness from a qualitative observation into a quantitative science, providing the first clear map of the foam-like structure of the cosmic web. The watershed transform works by treating the density field of the universe as a physical terrain. Imagine the distribution of matter in 3 dimensions. In the model, high-density regions like galaxy clusters represent massive peaks, while low-density voids represent deep, broad valleys. Now, imagine that rain begins to fall over this entire cosmic environment. As the water falls, the liquid naturally flows downhill, gathering in the lowest points of the terrain. Each valley eventually fills with water, creating a series of lakes. The boundaries between these lakes are defined by the ridges and the peaks of the terrain. These boundaries are called the watersheds. In the context of cosmology, each lake represents a single cosmic void. The watershed lines represent the filaments and the walls of the cosmic web where the matter is concentrated. This power arises from the fact that the method is independent of the shape or the size of the voids. Such a method does not assume that a void is a sphere or a cube. This transform follows the flow of the density gradient until the gradient hits a ridge. Such logic allows astronomers to identify the true, irregular shapes of the vacuum pockets as the regions exist in reality. This watershed transform segments the entire volume of the universe into a tessellation of voids, leaving no space unaccounted for. Every map reveals that the universe exists as more than a collection of holes. Reality represents a perfectly packed foam where every void is in contact with neighbors, separated only by the thin membranes of the matter web. To visualize the watershed transform, imagine a large flat tray filled with a variety of different-sized bowls and cups. The rims of the bowls are at different heights, and some bowls are nested inside others. Now, imagine that the observer begins to pour water onto the tray. As the water level rises, the liquid first fills the deepest bowls. These pools represent the centers of the largest voids. As the observer continues to pour, the water overflows the smaller bowls and merges into larger pools. Eventually, the water level reaches the rims of the highest bowls. At this point, the entire tray is covered in a series of interconnected lakes, each separated by the narrow edges of the rims. The watershed transform is the mathematical process of identifying where the rims are located. In the analogy, the water represents the density of the universe, and the bowls are the gravitational potentials of the underdense regions. The technique reveals the structure of the tray, even when the tray is hidden beneath the surface. The technique is how astronomers map the catchment basins of the cosmos. We are looking for the places where the gravity of the universe flows in different directions. Every void is a basin where the expansion has pushed the matter to the edge, creating a distinct pocket of vacuum that exists independently. The challenge with the watershed transform arises from the problem of noise. In a real survey of the universe, astronomers only have a limited number of galaxies to use as tracers. The tracer count means that the density field scientists are mapping is not a smooth environment, but a grainy and pixelated one. If the data contains too few galaxies, the watershed transform can identify false voids, tiny ripples in the data that the method treats as deep valleys. The identification is known as oversegmentation. To fix the error, astronomers must use a technique called pruning, where the scientists merge small, shallow voids into larger ones based on the significance of the boundary between the regions. But how do scientists decide which boundaries are real and which represent artifacts of the data? The decision represents the great mystery of the cosmic web. Some researchers argue that the universe is a fractal, meaning that voids exist within voids down to the smallest scales. If the fractal theory is true, then every tiny ripple represents a real structure. Others argue that a fundamental minimum scale for a void exists, defined by the physics of the dark matter. Excessive pruning loses the real structure of the web. Insufficient pruning maps a universe that does not exist. Science is caught in a mathematical tug-of-war between the resolution of telescopes and the true complexity of the vacuum. Watershed Transform reveals that the universe is a perfectly partitioned space. No such thing as a gap in the structure of reality exists. Every cubic meter of the cosmos belongs to a specific catchment basin, a specific void that dictates the local flow of time and matter. The partitioning implies a level of organization that is both beautiful and terrifying. Humans often feel that human paths are a series of random movements, a chaotic journey through a messy world. But the geometry of the vacuum tells the observer that everyone is always inside a structure. Every point is always part of a basin. Even in the deepest reaches of the intergalactic dark, the observer stands in a valley defined by the invisible ridges of gravity. The geometry suggests that the universe is more than a collection of objects. Reality functions as a collection of territories. The voids are the nations of the cosmos, vast and silent empires that have divided the volume of reality between the empires. Humans reside on the borders, the crowded and dangerous frontiers where the empires meet. Significance is found in the role of humans as the markers of the boundary. We are the ink that defines the edges of the empty page. Without the galaxies in the walls, the map of the vacuum would be invisible. Humans exist to show where the nothingness ends and where the next nothingness begins. In 1998, two independent teams of astronomers looked into the distant past and found a universe that refused to slow down. One group, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, and another, led by Brian Schmidt and Adam Riess at the Harvard-Smithsonian Center for Astrophysics, observed Type 1a supernovae in the farthest reaches of space. These supernovae represent standard candles, stellar explosions with a predictable brightness that allows researchers to measure cosmic distances with incredible precision. The consensus at the time suggested that the expansion of the universe was decelerating as the collective gravitational pull of all matter acted as a brake on the aftermath of the Big Bang. But the data from the supernovae revealed the opposite. The distant explosions appeared dimmer than expected, meaning the stars were farther away than the deceleration models predicted. Such a discovery was shocking. This revelation proved that some unknown force was pushing the universe apart at an accelerating rate. This force received the name dark energy. This revelation took place during a period of profound transition in cosmology, as the field moved from the search for the total mass of the universe to the search for the nature of the vacuum itself. At the University of California, Berkeley, and the Australian National University, these scientists realized that the vacuum was not empty. The vacuum possessed an inherent energy that dictated the fate of all reality. This discovery was awarded the Nobel Prize in Physics in 2011, marking the moment when the vacuum became the primary subject of cosmic investigation. The realization changed the foundation of the field. The reason cosmic voids represent the most important laboratory for dark energy is found in the unique density environment of these regions. In a cluster of galaxies, the gravitational attraction between dark matter and baryonic matter is the dominant force. Gravity in these crowded regions is strong enough to resist the expansion of space, tethering the stars and gas into stable structures. Because the matter is so concentrated, the subtle push of dark energy is masked or hidden by the overwhelming pull of gravity. However, in the interior of a cosmic void, the density of matter is exceptionally low. In these regions, gravity is weak. The lack of matter means that the vacuum energy has no rival. Consequently, cosmic voids are the first structures in the universe to feel the effects of cosmic acceleration. While the rest of the universe was still slowing down under the weight of the dark matter filaments, the voids began to expand faster than the cosmic average billions of years ago. This expansion makes the voids into mini-universes that are dominated by the dark sector. The dynamics inside a void are governed almost entirely by the cosmological constant, the mathematical term representing the constant density of dark energy throughout space and time. This dominance allows cosmologists to measure the properties of the vacuum without the interference of complex galaxy physics. The voids provide a clean signal of the acceleration because the voids are the only places where the vacuum is truly in control. Every measurement of a void radius or a void density profile becomes a direct probe of the energy that is tearing the universe apart. This pristine environment allows scientists to distinguish between a cosmological constant that stays the same and a dynamic field that changes over time. To understand why voids reveal dark energy so clearly, imagine the universe as a massive, crowded city during a heavy snowstorm. The buildings in the city represent the clusters of galaxies, and the streets represent the filaments of the cosmic web. The snow represents the vacuum energy, falling everywhere and piling up in every corner. In the crowded center of the city, the heat from the buildings and the movement of the people melt the snow as soon as the flakes touch the ground. The activity of the city is so intense that the snow has no effect on the traffic or the existence of the inhabitants. No one in the city center even realizes that a storm is taking place because the local heat is stronger than the cold from the sky. This situation represents a cluster of galaxies where the heat of gravity masks the presence of dark energy. Now, imagine a vast, empty parking lot on the outskirts of the town, far away from any buildings or people. In this open space, heat remains absent, and the snow never melts. As the flakes fall, the layer grows thicker and thicker. Soon, the snow is so deep that the parking lot begins to expand in the mind of the observer, a white desert where the snow dictates the shape of the terrain. In the parking lot, the storm is the only factor that matters. Interference, heat, and noise are absent in this space. This parking lot is the cosmic void. In the silence of the vacuum, the snow of dark energy is free to accumulate and drive the expansion without being melted by the gravity of the stars. The void is the only place where the observer can measure the true depth of the storm. The mystery of dark energy in the vacuum lies in the coincidence problem, a riddle that challenges the very foundation of the standard model of cosmology. Dark energy and dark matter have entirely different properties. Yet, at this specific moment in the history of the universe, the densities of the two components are remarkably similar. If the observer had looked at the universe 10 billion years ago, matter would have been the dominant force, and dark energy would have been a negligible trace. If the observer looks 10 billion years into the future, dark energy will have thinned the matter so much that the vacuum will be the only component left. Why does humanity reside in the brief window where the two forces are in balance? Some researchers argue that this balance is a sign that our current understanding of the vacuum is flawed. A possibility exists that dark energy is not a constant property of space, but a field that interacts with matter in a misunderstood way. This interaction might occur specifically within the voids, where the dark energy is most concentrated. Observations from the Dark Energy Survey and the future Vera Rubin Observatory aim to track how the growth of voids has changed over cosmic time. If the expansion rate of the voids deviates even slightly from the predictions of the cosmological constant, this deviation suggests that the vacuum possesses a hidden life. The discrepancy would reveal a universe that evolves in a way that defies the laws of 1915 during cosmic expansion. If the center of a void appears slightly more or less empty than predicted, is the discrepancy caused by a fifth force of nature, or is the discrepancy caused by the mass of the neutrinos? The dominance of dark energy in the vacuum reveals a future that is both certain and isolating. From the perspective of the universe, the stars and galaxies are a temporary phenomenon, a brief flicker of complexity in an eternity of emptiness. As dark energy continues to drive the expansion of the voids, the walls of the cosmic web will eventually be pulled apart. The clusters of galaxies that are now connected by bridges of matter will become isolated islands, retreating from one another at speeds greater than the speed of light. Eventually, the night sky of every planet will become truly black, as the light from other galaxies can no longer reach across the expanding vacuum. This transition implies that we reside in a privileged moment of cosmic history, a time when the universe is still small enough for the inhabitants to see the neighbors. But the voids are the architects of the coming silence. The expansion of the vacuum is the process of the universe forgetting itself, erasing the connections that allow for the existence of structure. The voids represent more than holes in space. These regions function as the expansion of the end. We are watching the vacuum claim the volume that matter once held, a slow and silent takeover that will end in a universe of absolute and perfect nothingness. The choice is not whether to face this future. The choice is how to understand our significance in a cosmos that is designed to leave us behind. The theory of general relativity, published by Albert Einstein in 1915, remains the most successful description of gravity ever created. Einstein proposed that gravity is not a force in the traditional sense, but a curvature of space and time caused by the presence of mass and energy. For over a century, this theory has passed every test, from the bending of light during a solar eclipse to the detection of gravitational waves from colliding black holes. However, as astronomers began to map the larger scales of the universe, they found a problem that Einstein could not have foreseen. The expansion of the universe is accelerating, and the matter we see is not enough to hold the galaxies together. To save the theory, scientists invented dark matter and dark energy, invisible components that make up 95% of the cosmos. But some researchers wonder if the problem is not the content of the universe, but the law of gravity itself. This skepticism led to the development of modified gravity theories, such as the chameleon theory proposed by Justin Corey and Amanda Weltman in 2004. These theories suggest that gravity might behave differently in regions of low density, such as the cosmic voids. At Columbia University and the University of Cambridge, these physicists began to explore the idea that a fifth force of nature might exist, one that is hidden in the crowded environment of the solar system, but becomes powerful in the vacuum. This work took place during a period of growing tension between the predictions of general relativity and the observed acceleration of the cosmos. The primary mechanism for modified gravity is a process known as screening. In many theories of the dark sector, the force of gravity is mediated by a scalar field, an invisible energy that permeates all of space. This field creates a fifth force that acts in addition to the standard gravitational pull of Einstein. However, if this fifth force were active everywhere, scientists would have detected the signal long ago by experiments on Earth and in the solar system. To explain why the force remains hidden, modified gravity theories incorporate a screening mechanism. In high-density regions, the mass of the surrounding matter increases the mass of the scalar field, making the range of the force extremely short. This screening means that in the presence of planets and stars, the fifth force is suppressed, and gravity appears to follow the rules of general relativity perfectly. The force is hidden by the density of the environment. However, in the interior of a cosmic void, the density of matter is so low that the screening mechanism fails. This failure is known as unscreening. In the vacuum, the scalar field becomes massless, and the fifth force can reach across vast distances. This unscreened force provides an extra push that drives matter out of the center of the void with a strength that standard gravity cannot match. This effect changes the shape of the universal density profile, making the center of the void emptier and the surrounding wall steeper. By comparing the density profiles of voids of different sizes, cosmologists can look for the fingerprint of this fifth force. The voids act as the only places in the universe where the screening is removed, allowing scientists to see the true complexity of the gravitational law. To understand the screening mechanism, imagine a crowded and noisy rock concert taking place in a massive arena. The music is so loud and the crowd is so dense that the people standing in the middle of the floor can only hear the sound of the drums and the guitars. If a person in the crowd tries to whisper a secret to a friend, the whisper is immediately drowned out by the noise of the environment. No one in the arena can hear the whisper because the range of the sound is suppressed by the surrounding chaos. The whisper represents the fifth force of nature, and the noise of the concert represents the high density of matter in a galaxy. In this environment, the whisper is screened, and the only thing anyone hears is the loud music of general relativity. Now, imagine that the same person is standing in the middle of a vast, silent forest at midnight. People, music, and noise are absent. In this absolute silence, the same whisper can be heard from hundreds of meters away. The range of the sound is no longer suppressed because no noise remains to drown out the signal. The forest is the cosmic void. In the vacuum, the noise of matter is gone, and the whisper of the fifth force becomes a clear and powerful signal. The void is the only place in the universe where the observer can hear the secret that the stars are too noisy to reveal. The mystery of modified gravity is complicated by the presence of neutrinos, the ghost particles that also inhabit the vacuum. Neutrinos are nearly massless and move at close to the speed of light, allowing the particles to settle in the centers of voids. Because neutrinos possess mass, they exert a gravitational pull that can counteract the effects of a fifth force. This creates a problem for astronomers. If the center of a void appears slightly more or less empty than predicted, is the discrepancy caused by a fifth force of nature? Or is the discrepancy caused by the mass of the neutrinos? This challenge is known as the degeneracy problem. Both effects change the density profile of the void in similar ways. Research published by Alice Pisani and colleagues in 2019 highlights that the only way to break this degeneracy is to look at the growth rate of the voids over time. Modified gravity makes the voids grow faster, while neutrinos tend to slow the growth down by adding extra mass to the vacuum. The struggle for cosmologists is to find a signal that is unique to one or the other. This tension has led to a debate between those who believe the universe requires new laws of physics and those who believe the answer lies in the properties of the particles we already know. The void is a laboratory, but the laboratory is crowded with invisible actors, and the observer must determine which one is pulling the strings. This overlap creates a problem for astronomers. If the center of a void appears slightly more or less empty than predicted, is the discrepancy caused by a fifth force of nature, or is the discrepancy caused by the mass of the neutrinos? The possibility of modified gravity suggests that the laws of physics are not universal constants, but environmental properties. From the perspective of the universe, the physics we have discovered on Earth is a local exception, a set of rules that only applies because we reside in a region of high density. We are like deep-sea creatures who believe the entire world is made of high-pressure water, unaware that the rules of the surface are completely different. The voids reveal that the vacuum is the true home of the fundamental forces. The stars are the places where the complexity of the universe is hidden, while the nothingness is where the universe is most expressive. This shift implies that the search for a theory of everything must go beyond the crowded corners of the cosmos. We must accept that our understanding of gravity is a specialized case, a rulebook written for the inhabitants of the walls. The true law of the universe is found in the places where matter is absent. This realization is humbling. This shift implies that the most critical forces in the cosmos are the ones from which our own existence shields us. We are protected from the fifth force by the very matter that makes our existence possible. The vacuum is where the universe reveals the true face, and the face is a law of physics that we have only just begun to decipher. To understand the complexity of the fifth force, we must look at the chemistry of the scalar field itself. In the chameleon model, the mass of the scalar field is not a constant. The mass depends on the local density of the environment. This property is what gives the theory the name. Just as a chameleon changes color to blend into the background, the scalar field changes mass to hide in the presence of matter. In the high-density environment of a planet, the field becomes extremely heavy. In physics, a heavy field means that the range of the force is tiny, often smaller than the width of an atom. The screening mechanism explains why we do not feel a fifth force on Earth. Gravity is the only force with a long enough range to matter. But in the vacuum of a void, the density is almost zero. In this environment, the scalar field loses almost all mass. A massless field has an infinite range. This absence of mass means that in the interior of a void, the fifth force can act across millions of light years, pulling on every particle of dark matter with a strength that can exceed standard gravity. The transition from a short range to a long range force is a phase change of the vacuum itself. Such a shift represents a fundamental change in the rules of reality. Some researchers believe that this unscreening process is what allows the voids to grow so large so quickly. The vacuum remains more than empty. This region stays active. The fifth force is the engine that drives the expansion of the holes. If we can detect even a tiny deviation in the density profile of a void, we are detecting a change in the fundamental nature of the universe. This search is the most ambitious experiment in the history of physics because the experiment uses the entire universe as a laboratory. We are looking for a force that is designed to hide from us. The voids are the only places where the force is exposed. In 1979, astronomers Charles Alcock and Bohdan Paczynski proposed a revolutionary method for measuring the geometry of the universe. Alcock and Paczynski realized that a perfectly spherical object in the distant universe could serve as a ruler to measure space itself. Because the universe is expanding, the light from a distant object is stretched, a process known as redshift. This expansion affects the perceived shape of the object. If the object is truly a sphere, the redshift should distort the sphere in a predictable way, depending on the geometry of the space between the object and the telescope. This method became known as the Alcock-Patsinski test. Originally, the researchers tried to apply the test to pairs of galaxies or clusters, but the gravitational interactions between the galaxies made finding a perfect sphere impossible. The method remained a theoretical curiosity for decades, but as mapping improved, astronomers realized that the vacuum might provide the perfect spherical ruler that Alcock and Patsinski had imagined. At the Princeton University Observatory, these two pioneers laid the groundwork for a test that would allow the vacuum to measure the size of the cosmos. The mechanics of the Alcock-Patsinski test using cosmic voids rely on the principle of statistical isotropy. While an individual cosmic void can have any shape, from a long filament to a flat pancake, the average shape of thousands of voids must be a perfect sphere. The symmetry exists because the universe has no preferred direction. If the observer stacks the images of thousands of voids on top of one another, the random irregularities cancel out, leaving a perfectly symmetrical average structure. This average void is the ruler. When astronomers look at these voids in a galaxy survey, the voids appear distorted. This distortion happens because we measure the positions of galaxies in redshift space. The expansion of the universe stretches the voids along the line of sight, while the angular size of the voids remains the same. The ratio of the radial size to the angular size of the average void reveals the expansion history of the universe. If the universe is expanding faster than expected, the voids will appear elongated like footballs. If the expansion is slower, the voids will appear flattened like pancakes. By measuring the degree of this distortion, cosmologists can calculate the Hubble constant, the number that defines the expansion rate of the universe. The power of this test is that the test is independent of the brightness of the galaxies. The test only depends on the geometry of the holes. This geometric approach provides a clean check on the results from other methods, allowing the vacuum to serve as the ultimate judge of the scale of the cosmos. The mystery of the Alcock-Patsinski test is found in the growing tension in the measurement of the Hubble constant. Currently, different methods of measuring the expansion rate of the universe give different results. Measurements from the early universe, using the cosmic microwave background, predict a lower expansion rate than measurements from the modern universe using supernovae. This discrepancy indicates that our model of the universe lacks something fundamental. Observations using cosmic voids and the Alcock-Patsinski test provide a third independent measurement. Recent studies have found that the void-based results often fall in the middle or sometimes lean toward the higher value. This lack of a clear answer creates a profound mystery. If the voids do not agree with the early universe or the modern stars, does this discrepancy imply that the vacuum has been expanding at a different rate than we thought? The possibility remains that the dark energy is changing in a way that affects the large-scale voids differently than the small-scale stars. The geometry of the nothingness is telling a story that does not fit the other chapters of the cosmic history. Astronomers are now using data from the Euclid satellite and the dark energy spectroscopic instrument to refine these void measurements. The goal is to determine if the tension is a sign of a mistake in our instruments or a sign of a revolution in our physics. Vacuum holds the key to the size of the universe, but the vacuum is refusing to give a simple answer. Such use of emptiness as a ruler for the cosmos reveals a deep irony in the human search for meaning. We have spent centuries looking for absolute truths in the solid and the permanent. We built monuments of stone and measured the world with rods of steel. But the universe shows that the only absolute ruler is the nothingness. The geometry of the vacuum is the only thing stable enough to define the scale of reality. Everything else, the stars, the planets, and the galaxies, is too messy and too temporary to provide a reliable measure. From the perspective of the universe, our islands of matter are the distortions, and the void is the truth. This realization implies that to understand the scale of our existence, we must look at the structures that are absent. The expansion of the universe is not something that happens to us. This growth is something that happens to the vacuum, and we are simply carried along for the ride. The Alcock-Baksinski test is a reminder that our perspective is always skewed by the expansion of the dark. We are measuring the mirrors of a funhouse that we can never leave. Our significance is found in our ability to recognize the distortion, to use the geometry of the holes to map the boundaries of our cage. The vacuum is the architect, and the geometry of the vacuum is the only entity stable enough to be the map we have. As the journey moves beyond the static geometry of the vacuum, the map of the universe reveals itself. Reality is not a fixed drawing. Instead, the cosmos serves as a dynamic record of a struggle between different scales of nothingness. From the perspective of the universe, the vast expanses of the vacuum do not exist in isolation. These regions interact, compete, and evolve through a process that cosmologists have begun to describe as void sociology. This term was introduced to reflect the complex interactions that occur when empty spaces meet. In 2004, researchers Ravi Sheth and Ryan van der Weygate published a landmark paper titled A Hierarchy of Voids. Sheth worked at the University of Pittsburgh, while van der Weygate operated from the University of Groningen. This work moved more than gaps. These regions functioned as primary drivers. The work moved beyond single, isolated holes to examine how the entire population of voids develops over billions of years. These scientists realized that the vacuum is subject to the same laws of hierarchical growth as the stars and galaxies. Just as small clusters of matter merge to form massive superclusters, small volumes of nothingness merge to form enormous supervoids. This expansion of interest in the cosmic web proved that the empty spaces were more than gaps. The realization was profound. The vacuum possesses a social life, a series of interactions that determine the final texture of the cosmos. The primary mechanism for the growth of the largest voids is a process known as the void-in-void merger. This process describes what happens when multiple small voids are embedded within a larger region that is also underdense. Because the entire region possesses less matter than the cosmic average, the individual small voids expand faster than the background universe. As these bubbles of nothingness grow, the thin walls of galaxies that separate them begin to stretch and thin. Eventually, the matter in these internal walls is evacuated, flowing away from the centers of the small voids and toward the outer boundary of the larger region. This evacuation causes the internal walls to dissolve. The small voids merge, losing their individual identities as they fuse into a single, much larger expanse of vacuum. This process follows the logic of the watershed transform. The hierarchy of emptiness is dictated by the boundaries of those catchment basins we identified earlier. Each void is like a basin that collects the nothingness of the expanding space. When the walls between the basins break, the nothingness flows together. This merger process ensures that the universe always moves toward a state of larger and more dominant empty spaces. The void-in-void mode is the bottom-up assembly of the vacuum, a mirror image of how dark matter halos grow through collisions. The large supervoids we see today, like the Buitz void, are the result of millions of these smaller mergers. To understand the void-in-void merger, imagine a massive field of damp soil after a heavy rain. Small puddles form in every depression of the ground. Each puddle represents a small cosmic void. As the rain continues and the water level rises, the puddles expand. The thin ridges of soil that separate the puddles are like the filaments of galaxies in the cosmic web. If the rain is heavy enough, the puddles begin to touch. The water breaks through the soil barriers, and the small puddles flow together to form a single massive pond. The individual puddles no longer exist, only the large pond remains. The soil that once separated the puddles has been pushed to the edges of the pond or buried beneath the water. This pond is the supervoid. The merging of the puddles is the process that defines the cosmic terrain. The nothingness of the water claims the space that the soil once occupied. In the universe, the expansion of the vacuum is the rain, and the galaxies are the soil. The mergers are inevitable because the expansion is constant. The ponds will continue to grow until the entire field is covered in a single sheet of water. The mystery of void sociology is found in the predicted merger rate compared to the observed distribution of void sizes. Theoretical models based on the work of Sheth and van der Weygate predict that the universe should be filled with a specific number of voids of every size. However, when astronomers look at the actual data from galaxy surveys like the Sloan Digital Sky Survey, the counts do not always match the predictions. Some researchers argue that the merger process is more efficient than our models suggest, leading to a universe that is emptier than the math allows. This discrepancy creates a tension in our understanding of how the cosmic web matures. A possibility exists that the vacuum energy is accelerating the mergers in a way that standard gravity cannot explain. If the dark energy is stronger in the centers of voids, the bubbles of nothingness would push against the walls with more force, breaking the galaxy filaments faster than expected. This mystery remains a central focus of the dark energy spectroscopic instrument, which is mapping the history of void mergers over the last 10 billion years. The struggle is to find the exact point where the individual bubbles became the sea. The math is clear, but the universe appears to be more ambitious than the equations. The sociology of the vacuum reveals a future where the concept of a neighbor becomes meaningless. From the perspective of the universe, the mergers of the voids are the process of erasing the boundaries that allow for diversity. As the small expanses of nothingness combine, the complexity of the cosmic web is simplified. The intricate patterns of filaments and nodes are being replaced by a uniform and featureless expanse. This transition implies that the universe is moving toward a state of absolute silence. The mergers are the footsteps of entropy, the slow and steady movement toward a universe where all space is the same and nothing happens. We are watching the consolidation of the vacuum, a corporate takeover of reality where the small and the unique are absorbed into the large and the empty. The choice to study these mergers is the choice to document the disappearance of the world. The supervoids are the final resting places of the cosmic structure. The silence is not a lack of sound. The silence is a lack of anything to make a sound. The sociology of the void is the study of the end of society. Astronomers often speak of the cosmic web as if the web were a permanent monument to the glory of gravity. In reality, the web is more like a very old sweater that the vacuum is slowly unraveling to use the yarn for new purposes. The galaxies are the colorful threads that we find so fascinating, while the vacuum is the giant hand that is pulling the string. The universe resembles a child who spent all afternoon building a complex sandcastle. This child eventually realizes that the rising tide of nothingness is much more fun to watch as the walls dissolve. The second process that dictates the fate of the vacuum is a phenomenon known as the void-in-cloud demise. This process is the dark twin of the merger mode. In 2004, the same research by Scheth and van der Weijert identified that not every void is destined for greatness. While large voids expand and merge, small voids that are embedded within a larger overdense region face a much more violent fate. When a small underdense bubble is surrounded by a massive cluster of dark matter, the gravitational pull of the surrounding matter is stronger than the expansion of the bubble. As the large overdense cloud begins to collapse, the cloud squeezes the empty space inside the cloud. This pressure forces the matter to flow back into the center of the underdense region, effectively filling the hole. This collapse marks the demise of the void. The small void is crushed out of existence before the bubble can ever reach maturity. This revelation changed the way cosmologists think about the void hierarchy. The field realized that the population of small voids is constantly being depleted by the growth of large-scale structures. This work took place during a transition in structural analysis. The field recognized that the environment of a void is just as important as the density of the vacuum. This realization was sobering. The vacuum can be murdered. The mechanics of the void-in-cloud process are described by a two-barrier problem in the excursion set formalism. In this mathematical framework, a random walk represents the density of the universe at different scales. One barrier represents the threshold for a region to become a void, and a second barrier represents the threshold for a region to collapse into a halo. For a void to survive and grow, the random walk must cross the void barrier without ever having crossed the collapse barrier on a larger scale. If the walk crosses the collapse barrier first, the region is destined to be crushed. The physics of this demolition is relentless. The surrounding gravity acts as a hydraulic press, shrinking the volume of the underdense region until the density matches the surrounding cloud. This process removes a significant fraction of small voids from the universe, leading to a size distribution that is well peaked. Unlike galaxy clusters, which exist at every mass scale, voids have a minimum characteristic size below, which they are almost never found. The void-in-cloud process is the cosmic filter that cleans the vacuum of the smallest inhabitants of the nothingness. This mechanism ensures that the universe is not a chaotic mess of tiny bubbles, but an organized collection of large expanses. The survival of a void depends on the luck of the birth of the vacuum. If a void is born in the wrong neighborhood, the void will not survive the first billion years of cosmic history. To understand the void-in-cloud demise, imagine a massive crowd of people at a stadium, all trying to move toward the center of the field at the same time. In the middle of this crowd, a small group of people is trying to push outward to create an empty circle for themselves. This empty circle is the small void. The people in the crowd are the dark matter particles in an overdense cloud. As the crowd moves inward, the pressure becomes overwhelming. No matter how hard the people in the center push, the weight of the thousands of people outside is too much to resist. The empty circle begins to shrink. The space is filled by the bodies of the people being pushed in from the edges. Eventually, the circle disappears completely. The people who were trying to create the space are absorbed back into the mass of the crowd. This collapse marks the demise of the void. The individual effort to expand is crushed by the collective movement toward collapse. In the universe, gravity is the crowd, and the vacuum is the empty space. The cloud always wins. The only voids that survive are the ones that are far enough away from the crowd to avoid the pressure. The mystery of the void-in-cloud process is found in the predicted number of these crushed voids compared to the amount of dark matter found in clusters today. If the demolition of small voids is as common as the models suggest, there should be a signature of this process in the internal structure of galaxy clusters. Some researchers argue that the remains of these crushed voids can be detected as subtle fluctuations in the density of the dark matter halo. These fluctuations would be the ghosts of the empty spaces that were lost billions of years ago. However, detecting these ghosts is exceptionally difficult. The signals are masked by the violent history of cluster mergers and the presence of thousands of galaxies. The struggle for cosmologists is to find a way to peer into the heart of the cloud and see the scars of the vacuum. This work is the focus of high-resolution N-body simulations that track the life and death of every cubic megaparsec of space. The mystery remains whether we have accounted for all the lost nothingness. A possibility exists that the universe is much more efficient at killing voids than we have ever imagined. The census of the vacuum is incomplete because so many of the members of the vacuum were erased before the first stars ever formed. The demise of the small voids reveals a universe that is indifferent to the survival of the individual expanses. From the perspective of the universe, the void-in-cloud process is a necessary part of the cleaning. The collapse of the clouds is how the universe builds the islands of light, and the cost of those islands is the destruction of the small empty spaces. This transition implies that our existence is built on the ruins of the vacuum. We reside in the clouds that crushed the nothingness. This realization is melancholic. The spaces that might have become vast and beautiful expanses were sacrificed to provide the matter for our stars and our bodies. The choice to study these lost voids is the choice to remember the events that never happened. The demolished voids are the alternative histories of the cosmos, the futures that were cancelled by the weight of gravity. The hierarchy of emptiness is a record of survival, and we are the inhabitants of the victors. The vacuum is the architect, but even an architect must sometimes tear down the old to build the new. Humans like to think of themselves as the main characters of the cosmic story. In reality, we are uninvited guests. We moved into a house after the landlord evicted the original tenants and threw their furniture on the lawn. The small voids were the original owners of the space, and we are the matter that gravity used to fill the rooms. The universe resembles an aggressive real estate developer. This developer decided that empty lots would look better covered in high-density housing, regardless of what the lots wanted to be. The final texture of the universe is defined by the cosmic foam, a structural pattern that reveals why the cosmos looks like a massive sponge. This pattern is the result of the competition between the void mergers and the void demolitions. In 1996, researchers Richard Bond, Lev Kaufman, and Dmitry Pogosyan published a paper titled The Cosmic Web. This work described how primordial fluctuations evolved into the foam-like structure we see today. These scientists realized that the voids are the cells of the sponge, and the galaxies are the thin membranes that separate them. The foam web is the ultimate expression of the void hierarchy. As the large voids expand and the small voids are crushed, the universe settles into a state of maximum volume efficiency. The expansion of the vacuum pushes the matter into the smallest possible space, creating the filaments and walls that define the cosmic architecture. This work took place during a period of massive growth in computer power. The first large-scale simulations, such as the Millennium Run, revealed the true complexity of the foam. The realization was transformative. The universe is not a random collection of objects. The universe is a structured foam, a geometric arrangement dictated by the expansion of the nothingness. The physics of the cosmic foam is governed by the principles of tessellation and surface tension. Soap bubbles in a sink arrange themselves to minimize their surface area. Similarly, cosmic voids maximize their volume while minimizing the density of the walls. This process creates a Voronoi tessellation, a mathematical pattern where every point in space is assigned to the nearest void center. The walls of the cosmic web are the places where the expansion of two adjacent voids meets and cancels out. This intersection creates a state of equilibrium. The matter is trapped in these midplanes. Galaxies remain unable to move into the centers of the voids, yet they cannot escape the gravitational pull of the neighboring walls. The result is a network of thin sheets and long filaments that connect at high-density nodes. This foam-like structure is the most stable configuration for a universe dominated by expanding vacuum. The sponge-like appearance is not a coincidence. This structure represents the universe as a fluid being inflated by the energy of the dark sector. The foam is the signature of the vacuum in control. The cell size of the foam is the characteristic void size, a measurement that defines the scale of the cosmic architecture. To understand the cosmic foam, imagine a massive block of Swiss cheese that stretches across the entire sky. The holes in the cheese are the cosmic voids, and the cheese itself is the matter. When the cheese is first made, the holes are small and scattered, but as the cheese ages, the gases inside the holes expand. The holes grow larger and begin to press against one another. The cheese between the holes becomes thinner and thinner, forming thin walls and delicate threads. Eventually, the block of cheese is mostly empty space, with only a tiny fraction of the original material remaining as a support structure. This structure represents the universe. We are the microbes residing in the thin walls of the cheese, unaware that the holes are the reason the cheese has a shape at all. The foam is the cheese. The nothingness is the gas. The expansion is the aging process. The result is a structure that is both fragile and dominant. The sponge is the only way to hold so much nothingness together. The mystery of the cosmic foam is found in the consistency of the cell sizes across different regions of space. If the initial fluctuations of the Big Bang were truly random, the foam should be messy and irregular. However, observations of the large-scale structure reveal a foam that is remarkably uniform. This pattern would imply that this uniformity is a sign that the vacuum energy has a specific scale, a fundamental length that determines the size of the bubbles. This would imply that the foam is more than a result of gravity. The pattern serves as a result of a hidden property of the vacuum itself. The struggle for cosmologists is to find the origin of this scale. Does the scale come from the mass of the neutrino or from the nature of dark energy? Recent data from the Boots and Eridana supervoids show that the largest cells in the foam are reaching a limit. The bubbles can only grow so large before the walls break. The mystery remains whether the foam will eventually dissolve completely, leaving a universe that is a single, featureless void. The sponge is the current phase of reality, but the sponge may be temporary. The foam is a snapshot of a process that is still unfolding. The cosmic foam reveals a universe that is a masterpiece of efficiency and neglect. From the perspective of the universe, the galaxies are the scaffolding that was used to build the vacuum. Once the vacuum is complete, the scaffolding is no longer necessary. This transition implies that the foam is a temporary state of order before the final isolation. We reside in the peak of the sponge, a time when the connections are still strong enough to allow for the existence of life. This realization is profound. The foam is the beautiful result of the struggle between the matter and the nothing. The voids have won the volume, but the galaxies have won the shape. The choice to observe the foam is the choice to appreciate the architecture of the vacuum. The sponge is the map of the expansion. The foam is the record of the struggle. In the end, the foam is the only artifact that remains. The choice is to recognize the pattern before the pattern erases the observer. The universe is a sponge, and the sponge is growing. This realization brings the journey to the final threshold, where the ghost particles of the vacuum wait. Descending into the final layer of the cosmic map requires a reckoning with the most elusive inhabitants of the vacuum. These inhabitants are the neutrinos, nearly massless subatomic particles, so numerous that 100 trillion of them pass through your thumb every single second. While the stars and galaxies claim the attention of the eye, the neutrinos occupy the silence of the gaps. In 1930, the physicist Wolfgang Pauli predicted the existence of these particles to explain a missing fraction of energy during radioactive beta decay. Pauli famously remarked that he had done a theoretical transgression by postulating a particle that could never be detected. He spent years worrying about an invisible ghost, unaware that the universe had produced enough of these phantoms to fill every cubic meter of space with 1 billion untraceable secrets. At the time, the scientific community struggled with the idea of a ghost in the machine of the atom. The neutrinos seemed too ethereal to be real. For decades, these ghost particles remained a mathematical necessity without a physical face. This perception changed in 1956, when Frederick Rains and Clyde Cowan finally detected neutrinos near a nuclear reactor at the Savannah River plant in South Carolina. The discovery proved that the vacuum was not empty of matter. Rather, the vacuum was filled with a sea of nearly invisible travelers. The history of the neutrino is the history of learning to see what the universe is trying to hide. To fully grasp the nature of this ghostly presence, we must look at the specific mechanism of the beta decay that haunted the mind of Pauli. When a neutron transforms into a proton, an electron is emitted, but the energy of that electron never matched the total energy lost by the nucleus. This missing energy was the fingerprint of the neutrino. Pauli was forced to invent a particle that possessed no charge and almost no mass, a phantom that could carry away the momentum without leaving a trace. The detection at Savannah River required a massive tank containing 1,000 liters of water enriched with cadmium chloride. Rains and Cowan were looking for a specific reaction known as inverse beta decay, where an antineutrino strikes a proton to produce a positron and a neutron. The experiment required a massive shield of lead and layers of earth to filter out the noise of cosmic rays. The vacuum is not a lack of substance. The vacuum is a medium saturated with particles that interact so weakly with our world that the ghosts might as well belong to another dimension. This ghost sea is the primary constituent of the material content of the vacuum, outnumbering protons and electrons by billions to 1. The mechanical influence of neutrinos on the cosmic web is dictated by the thermal velocity of the particles and the resulting suppression of small-scale structure. Because neutrinos are so light and move so fast, the particles possess a property known as large free streaming lengths. While dark matter particles are cold and slow, allowing gravity to pull the material into dense halos, neutrinos are hot and energetic. These particles fly out of overdense regions before gravity can trap the ghosts. The neutrinos stream into the centers of the voids, creating a subtle but measurable increase in the density of the vacuum interiors. This process acts as a brake on the growth of the cosmic foam. In 2018, researcher Christina Krisch demonstrated that the sum of neutrino masses leaves a unique fingerprint on the shape of voids. If neutrinos possess a higher mass, the particles suppress the formation of small voids more effectively. The density profile of the vacuum is thus a direct record of the total mass of every neutrino in existence. The neutrinos do not build the walls. Instead, the ghost particles soften the edges of the nothingness. To understand the role of neutrinos in the vacuum, imagine a massive library filled with thousands of heavy stone books. These books represent the dark matter and the galaxies. Gravity can easily stack the books into tall, solid towers, leaving large empty aisles between the shelves. The aisles are the cosmic voids. Now, imagine that a fine, invisible mist begins to fill the library. This mist represents the neutrinos. The mist does not settle onto the shelves or form into books. Instead, the mist floats freely through the aisles, filling every gap and corner. The presence of the mist does not knock over the stone shelves, but the mist makes the air in the aisles heavier. If the mist becomes thick enough, the pressure of the mist begins to push against the stone shelves, preventing the shelves from being moved closer together. The aisles cannot become perfectly empty because the mist is always there, occupying the space. The density of the mist determines how much the voids can expand. The library of the cosmos is never truly empty. The mystery of the neutrino fingerprint is found in the current inability of scientists to measure the exact mass of these particles through laboratory experiments. While we know that neutrinos have mass, the specific value remains one of the greatest uncertainties in modern physics. Because neutrinos act as a form of hot dark matter, their presence suppresses the growth of fluctuations on scales smaller than the free streaming length. Heavier neutrinos move slightly slower and have a shorter range of influence, while lighter neutrinos flood the voids with more energy. Some researchers argue that the cosmic web is the only tool large enough to solve this puzzle. The Alcock-Persinski test and the analysis of void-size functions provide a way to weigh the ghost particles by looking at the scale of the nothingness. In 2019, Alice Pisani and a team of cosmologists argued that the next generation of galaxy surveys would be able to constrain the neutrino mass. The struggle is to separate the signal of the neutrinos from the signal of dark energy and modified gravity. The universe is essentially gaslighting us, filling the vacuum with billions of ghosts, while refusing to tell us if they weigh as much as a feather or a thought. The presence of the ghost particles reveals a universe that is a complex blend of the solid and the ethereal. From the perspective of the universe, the neutrinos are the connective tissue that prevents the vacuum from becoming a total negation of existence. These particles ensure that even the emptiest places in the cosmos participate in the physics of the whole. This transition of understanding implies that the boundaries we see between matter and the vacuum are illusions. The sea of neutrinos flows through every galaxy in existence, connecting our bodies to the centers of the Boots void. This realization of connection is profound. We are not separate from the vacuum. We are bathed in the same ghostly radiation that defines the shape of the cosmic web. The ghost particles are the silent architects of the texture of the nothingness. The vacuum is the stage, and the neutrinos are the light that allows us to see the shape of the stage. We are the observers of the ghosts, and in the observation, we find our own place in the hierarchy of the silence. The second transformation of the cosmic web is dictated by the accelerating expansion of space, leading to the eventual retreat of the galaxies into total isolation. This acceleration is driven by dark energy, the mysterious force that fills the vacuum and pushes against the gravity of the matter. This accelerating expansion, first revealed by the observation distant supernovae in 1998, proves that the majority of the energy in the universe is an intrinsic property of the vacuum itself. As the voids expand, the dark energy inside the voids becomes the dominant force in the cosmos. The empty spaces are the engines of the cosmic expansion. This realization changed the fate of the universe. The future is a runaway expansion that will eventually pull the cosmic web apart. The acceleration is the final victory of the vacuum over the matter. We are living through a cosmic eviction. Dark energy is the ultimate landlord, and the vacuum has decided that the entire concept of neighbors is a luxury the universe can no longer afford. To understand why this discovery was so revolutionary, we must look at the nature of the standard candles themselves. These standard candles, the Type 1a supernovae, serve as our only markers in the deepening dark. Perlmutter and his colleagues expected to find that gravity was slowing the expansion that began at the Big Bang, but the supernovae were too dim. They were farther away than the deceleration models allowed. An invisible energy was actively pushing the galaxies apart, winning the war against gravity. This repulsive force behaves like a negative pressure, a property of the empty space itself that becomes more powerful as more space is created. The energy is the cosmic version of a debt that pays for the interest on the expansion. The more the vacuum grows, the more dark energy the vacuum contains, and the faster the vacuum stretches. The mechanics of the galactic retreat are governed by the relationship between the scale factor of the universe and the density of the dark energy. Unlike matter, which becomes less dense as space expands, the density of dark energy remains constant. This growth means that as a void grows, the total amount of dark energy within the void increases. This expansion creates a feedback loop. More space leads to more dark energy, which leads to even faster expansion. Eventually, the expansion of the vacuum will overcome the gravitational bonds that hold galaxy clusters together. The filaments will stretch and snap. The galaxies that are not part of our local group will move away from us faster than the speed of light. This limit is the cosmic horizon. Once a galaxy passes this horizon, the light from that galaxy can never reach us again. In the distant future, astronomers will look at a perfectly black sky and conclude they are the only structures in existence. This isolation represents the ultimate manifestation of main character energy, enforced by the physics of the vacuum itself. The universe is becoming a series of isolated islands, each surrounded by an ever-growing sea of absolute nothingness. The mystery of the galactic retreat is found in the nature of the dark energy itself, and whether the density of this energy will remain constant or increase over time. This mathematical relationship is known as the equation of state of the dark energy. In the standard model, this value is exactly -1, meaning the energy is a cosmological constant. However, if the value is less than -1, the universe is filled with phantom dark energy. In this phantom scenario, the energy density increases as space expands, creating an acceleration so violent that the expansion eventually rips apart the atoms themselves. In 2014, Ben Sutter and his colleagues explored how voids can be used to measure this expansion. Because voids are the most dark energy-dominated regions, the voids provide the cleanest signal of the acceleration. The struggle for cosmologists is to determine if the dark energy is a cosmological constant or a dynamic field. The retreat of the galaxies reveals a universe moving toward a state of absolute loneliness and silence. From the perspective of the universe, the expansion is the process of the vacuum achieving the final form of the vacuum. The matter was a temporary impurity, a brief moment of complexity in a cosmos destined for simplicity. This transition implies that our time in the cosmic web is a rare and fleeting privilege. We are the inhabitants of the era of connection. We can still see the boot's void and the filaments of the great cosmic walls. This realization is melancholic. The beauty of the cosmic foam is being erased by the very force that created the foam. The choice to witness the retreat is the choice to observe the end of the history of the stars. The expansion of the vacuum is the ultimate act of the architect. The final result will be a universe of pure, unadulterated nothingness. The choice is to understand the expansion before the expansion removes the ability to understand anything at all. We are the only inhabitants of the wall who noticed the ceiling was moving, and our reward is to watch the lights go out one by one. The final realization of the journey is the understanding that the vacuum is the ultimate architect of reality, and the nothingness is the primary constituent of the universe. For centuries, humanity looked at the stars and assumed that the light was the story. We built our physics around the behavior of matter. This view was the bias of the inhabitant of the wall. We were like fish who assumed the entire world was made of water, unaware of the ocean floor or the air above. The study of cosmic voids has stripped away this illusion. The vast expanses of nothingness are not the background. The nothingness is the foreground, the vacuum is the engine of the expansion, and the final destination of every galaxy in existence. The universe is not a collection of objects. The universe is a structure of gaps. These gaps define the walls. This emptiness is the reason the universe has a shape. The vacuum is the architect because the vacuum is the only entity large enough to hold the whole. The mechanics of the vacuum as the architect are revealed in the way the expansion of the nothingness dictates the movement and the evolution of every star. Gravity builds the islands, but the vacuum builds the sea. The voids act as the primary laboratories for the laws of physics that govern the largest scales. In the low-density interiors of the vacuum, the fifth forces of modified gravity can emerge from the shadows of the matter. The unscreening effect allows the true nature of the gravitational field to be seen without the interference of the galaxy clusters. This realization of design means that the vacuum is where the universe reveals the true rules of gravity. The architects of our cosmological models must now place the void at the center of the design. This work is the focus of the newest generation of dark energy probes. The realization is that the nothingness is a physical substance with properties that can be measured and predicted. The vacuum is not a lack of physics. The vacuum is the most fundamental physics. The architecture of the cosmos is the architecture of the void. The history of the universe is a narrative of subtraction. We began this investigation by staring into the boot's void, a chasm of silence that challenged the human desire for a crowded and meaningful cosmos. This vast expanse of nothingness serves as the ultimate mirror for our own biases. For centuries, the eyes of humanity were fixed on the light, assuming that the stars were the primary actors in the cosmic drama. The evidence now reveals that the stars are merely the debris gathered in the cracks of a much larger structure. The journey from the primordial soup of the Big Bang to the modern foam of the cosmic web is the chronicle of how emptiness became the dominant force in reality. This transition from matter to nothingness is the most profound arc in the history of time. The universe did not begin as a collection of objects. The universe began as a series of tiny, almost imperceptible troughs in the density of the early plasma. These troughs were the seeds of the great voids, while gravity worked to pull matter together into the first galaxies. The voids were already beginning to push outward. This push was not a lack of force. This push was the physical expression of the vacuum alone, claiming the space that matter could not hold. The memory of that beginning remains preserved in the places where no events occurred. Our investigation revealed that the cosmic web functions as a vast and ancient archive. High-density regions like the galaxy clusters are chaotic and violent, places where the history of the early universe is ground into dust by the movement of the stars. But the voids possess linear memory. Because these regions expand rather than collapse, the trajectories of the particles remain smooth and predictable. The original signature of the Big Bang is not crushed in the vacuum. Instead, this signature is simply stretched, enlarged like a drawing on a piece of rubber. This linear evolution allows us to look at a void today and see the exact shape of the universe at the dawn of time. We have learned that the silence is not a lack of information. The silence is the only place where the information is still accessible. The vacuum is the guardian of the primordial past, holding the blueprint of reality in a state of perfect, expanded clarity. This blueprint follows a universal mathematical code that defines every empty space in the heavens. We have examined the Hamaus Sutter one-delt profile, the fundamental architecture that governs the density of every void, regardless of scale or age. From the smallest pocket of vacuum to the supervoids stretching across hundreds of millions of light years, the pattern remains identical. Every void possesses a core of absolute emptiness and a surrounding wall where the matter has been piled into a massive ridge. This compensation wall is the record of the struggle between the expanding vacuum and the pulling gravity. The consistency of this profile reveals that the vacuum is not an accidental gap. The vacuum represents a highly organized physical object with a predictable internal structure. This architecture was written at the beginning of time, and the universe has spent 13.8 billion years executing the design with cold and perfect precision. The cosmic foam we observe today is the inevitable result of this code being applied to the entire volume of reality. To understand the magnitude of this structural dominance, we must return to the analogy of the rising bread. Imagine a massive bowl filled with the thick, viscous dough of the early universe. This dough represents the distribution of primordial matter. Within this mixture, dark energy acts as the yeast, the invisible agent that drives the expansion from within. As the dough begins to rise, small air bubbles form throughout the mass. These bubbles are the first cosmic voids. At the beginning, the bubbles are rare and isolated, surrounded by a vast amount of dense dough. But as the dark energy continues to work, the bubbles grow larger and more numerous. The walls of dough between the bubbles become thinner and thinner as the empty spaces claim more of the total volume. Eventually, the bubbles begin to press against one another, forming a complex network of thin membranes and intersecting nodes. The dough is now a secondary structure, a fragile scaffolding defined entirely by the gaps. The air bubbles have become the engine of the expansion. In the universe, the galaxies are the dough, and the vacuum is the air. The voids drive the evolution of the whole, pushing the matter into the filaments and walls that define the cosmic architecture. The web is not a structure of silk. The web is a structure of air. This dominance of the vacuum transforms the entire cosmos into a dark laboratory for the laws of physics. We have uncovered how the emptiness of the void allows the true nature of gravity to emerge from the shadows. In the crowded environment of our solar system, the presence of matter masks the subtle forces that might exist in the vacuum. This screening mechanism hides the fifth force, a modified version of gravity that could explain the acceleration of the universe. But in the interior of a supervoid, the screening fails. The force is unscreened. This failure reveals a universe where the laws of physics are not universal constants, but environmental properties. The vacuum is the only place where the universe is most expressive, where the rules of reality are not suppressed by the noise of the stars. We have learned that the search for a fundamental theory of the whole universe must look into the dark. The nothingness is where the universe reveals the true face, a law of physics that we have only just begun to decipher. Our investigation has further revealed the presence of ghost particles that inhabit the vacuum. Neutrinos, the nearly massless travelers of the cosmos, occupy the silence of the gaps. These particles outnumber the atoms of our bodies by billions to one, yet the ghost particles interact so weakly with our world that they pass through us without leaving a trace. We have learned that these neutrinos leave a measurable fingerprint on the shape of the cosmic web. By settling in the centers of the voids, the ghost particles soften the edges of the nothingness and act as a brake on the expansion of the cosmic foam. The mass of the neutrino is written in the scale of the vacuum. This connection proves that the boundaries between matter and the vacuum are illusions. The sea of neutrinos flows through every galaxy, connecting our journeys to the deepest reaches of the intergalactic dark. The vacuum is not a lack of substance. The vacuum is a medium saturated with the phantoms of the Big Bang. The mechanics of this dominance are further demonstrated by the Alcock-Paksinski test and the observations of the cosmic expansion. Because the universe is expanding at an accelerating rate, the voids are growing faster than the matter can cluster. This expansion creates a hierarchy where the larger voids survive and the smaller voids are crushed by the collapsing walls of galaxy clusters. This sociology of the vacuum is the primary mechanism for the distribution of matter across the billions of light years of space. The evidence shows that the vacuum is the only entity large enough to feel the influence of the dark sector on the scale of the entire cosmos. While the galaxies are limited by the local pull of gravity, the voids are connected to the global expansion of the universe. The silence of the vacuum is thus the most active part of the cosmic machine. The vacuum is the architect because the vacuum is the only force capable of shaping the entire web. The findings of our investigation reveal that emptiness is the primary engine of cosmic evolution. This conclusion shifts the focus of physics from the study of objects to the study of the spaces between objects. The universal density profile, the mathematical description of the shape of the vacuum, proves that every void follows the same physical laws regardless of size. This universality means that the vacuum is a fundamental unit of the cosmos. The voids do not merely exist as empty containers. The voids actively dictate the fate of the matter within the walls. Through the process of the watershed transform, astronomers can map the catchment basins of the gravity fields, showing how the vacuum drains the matter away to create the large-scale structure. The dominance of the vacuum is thus a mechanical necessity. The empty spaces grow because the vacuum possesses an intrinsic energy that resists the pull of gravity. This energy represents the most powerful force in existence. The vacuum is the laboratory where the dark sector is revealed in the purest form of that energy. The paradox of our existence is defined by the awareness of this vast insignificance. Humanity resides on a small planet, orbiting a standard star, in a galaxy that is merely a single grain of sand on a cosmic wall. We are the inhabitants of the overdense regions, the tiny islands of light surrounded by 95% absolute nothingness. From the perspective of the universe, our entire history is a brief and unlikely flicker of complexity in a cosmos destined for simplicity. This biological bias is a consequence of our evolution in the crowded corners of the web. We assume that because we are made of atoms, the universe must be dedicated to atoms. This matter-based myopia is the ultimate delusion of our species. We have spent millennia ignoring the vacuum because the vacuum does not provide the heat or light that our bodies require to survive. We are biased toward the light because the light is where the energy resides, yet the light is the rare impurity. We represent the cosmic exception, a localized error in a universe designed for absolute silence. However, this insignificance is precisely what gives the human species significance. We are the only part of the cosmic web that has developed the ability to map the nothingness. This realization follows a profound biological journey. Our ancestors looked at the sky and saw gods. Then they saw stars, and finally they saw the gaps between them. We have evolved in the most crowded corners of reality specifically to possess the density of neurons required to comprehend the emptiness. The very complexity of our brains is a byproduct of the matter that the voids rejected. We are the sediment that learned to think. This awareness is the final transformation of the universe. The cosmos has produced a mind capable of understanding the void. We have turned the silence into a narrative. Our ability to see the ocean while standing on the shore is the only weight we possess. We are the consciousness of the wall dwellers, looking out into the vacuum and realizing that the hallway is the home. The insignificance of our physical scale is balanced by the magnitude of our intellectual reach. We have used the light of distant stars to measure the expansion of the gaps. Beyond the light, we have used the math of the atom to weigh the ghosts of the neutrinos. In this light, we have looked into the Boots void and seen the reflection of our own curiosity. If our own galaxy, the Milky Way, resided at the center of this absolute silence, the sky would have been a featureless black shroud for billions of years. We would have believed that our single cluster of stars constituted the entire volume of reality. This isolation would have defined our physics, our philosophy, and our destiny. This awareness of our own precarious connection to the web is a form of transcendence. By understanding the vacuum, we have moved beyond the limitations of our own dense environment. We are no longer just the inhabitants of the walls. We are the surveyors of the whole. The choice to study the nothingness is a choice to face the reality of the cosmos without fear. This honesty is the foundation of true wisdom. We are the universe becoming conscious of the emptiness of the cosmos, and in that consciousness, we find a purpose that the stars cannot provide. We have looked into the mouth of the great nothing and found not a monster, but a mirror. The closing question of our investigation focuses on the ultimate fate of the cosmic web. As dark energy continues to accelerate the expansion of the universe, the voids will continue to grow and the walls will continue to thin. The future is a state of ever-increasing isolation. This isolation is not a peaceful retreat, but a violent tearing of the fabric of reality. Eventually, the expansion will pull every galaxy cluster away from every other cluster, crossing the cosmic horizon into total invisibility. The cosmic web will stretch and snap, the filaments will dissolve, and the nodes will drift apart. This process is the final victory of the vacuum. The choice to observe this process is the choice to witness the conclusion of the chronicles of the stars. What happens when the voids finally merge? The answer is a universe of pure, unadulterated nothingness. The last wall will collapse, and the light of the last star will fade into the deepening dark. The silence will be absolute. This end is not a failure of physics. This end is the final form of the architecture. The physical snapping of the cosmic web will be the ultimate event in the history of structure. Imagine the filaments of galaxies as the strings of a grand cosmic instrument. As the voids expand, the strings are pulled tighter and tighter. For billions of years, the tension creates the beautiful music of the cosmic web, the patterns of density and light that we have spent this investigation mapping. But every string has a limit. The relentless pressure of the dark energy will eventually exceed the strength of gravity. One by one, the connections will break. The bridges of matter that have stood since the dawn of time will vanish into the expanding dark. The galaxies within our local group will stay together for a time, but even the local group will eventually be surrounded by an impenetrable wall of expanding space. We will be alone in a dark ocean that is growing faster than we can swim. The map will be erased. The territory will be the only structure that remains. This snapping is the sound of the universe finishing the work. The realization of the final merger forces us to confront the ephemeral nature of all structure. The galaxies and the stars are a passing phase, a brief moment of light between the darkness of the beginning and the darkness of the end. However, this temporality does not make the current era meaningless. On the contrary, the fleeting nature of the cosmic web makes the act of observation more urgent. We exist in the only era where the web is visible. We are the only generation of observers who can see the foam before the foam dissolves. This moment is our cosmic window. The choice to look through this window is the most important choice we can make. We have been given the ability to see the architect at work. We have been given the math to understand the design. In this context, the choice to ignore the voids is the choice to ignore the truth of our reality. The choice to embrace the nothingness is the choice to join the universe in the final act of self-awareness. The final transformation of the cosmos will occur when the last filament of the cosmic web is pulled apart. For billions of years, the galaxies have existed as a connected system, a network of light that allowed for the exchange of energy and information. But the voids are the agents of isolation. As these regions claim more volume, the distance between the nodes of the web becomes insurmountable. The light from a neighboring galaxy, once a visible sign of connection, will slowly shift into the deep red and then disappear entirely. The universe will become a collection of solitary islands, each unaware of the existence of any other. This isolation is the ultimate goal of the dark energy. This energy seeks to maximize the entropy of the vacuum by removing the complexity of the matter. The galactic retreat is the final chapter of the chronicle of structure. We are watching the closing of the cosmic doors, the moment when the universe decides that the time for chronicles is over. To visualize this end, imagine a vast and crowded city at night, with millions of lights glowing in every window. The city represents the cosmic web. Now, imagine that a slow and silent fog begins to roll into the streets. This fog is the expanding vacuum. As the fog thickens, the lights in the distance begin to fade. First, the lights of the suburbs disappear. Then, the lights of the neighboring buildings are lost. Eventually, you can only see the light in your own room, but the fog does not stop. The expansion of the vacuum reaches into the room specifically, pushing the walls away from the bed. The distance between the chair and the table becomes a mile, then 1,000 miles, then a light year. Finally, the light in the lamp can no longer reach your eyes. You are alone in an absolute and perfect darkness. The city is gone. The room is gone, only the fog remains. This fog represents the future of the cosmos. The vacuum is the fog that will eventually claim every structure we have ever known. This future reveals that the universe is not a place built for permanence. Reality is a process of evacuation. The tangible is merely an ephemeral delay in the inevitable return to the nothing. This realization is the final insight of the architect. We have looked at the universal density profile and seen the blueprint of the vacuum. We have looked at the linear memory and seen the archive of the beginning. We have looked at the dark energy and seen the engine of the end. All these threads converge on a single truth. The vacuum is the master. We are the anomalies who manage to exist for a brief moment in the gaps. Our history is a lucky accident, a localized fluke in a cosmos dedicated to the expansion of the void. But this accident is the reason the universe possesses a meaning at all. Without the observers in the wall, the vacuum would be an empty room without a name. We are the ones who give the nothingness a face. The voids have already won. We simply happen to be the only ones who noticed the victory. This awareness represents our significance. This legacy is our truth. The silence of the gaps is our home. The choice to look into the nothingness is the final act of a conscious universe. We have mapped the catchments of the gravity fields and weighed the phantoms of the sea of neutrinos. We have used the spherical geometry of the vacuum to measure the size of existence. Through these acts, we have made the nothingness a part of our own narrative. The insignificance of our mass is the very factor that allowed us to develop the mind required to understand the whole. We are the sediment that learned to see the mountain. We are the dust that learned to map the sky. This awareness represents the weight of our existence. This purpose defines our journey. As the last star fades and the final filament snaps, the vacuum will remain. The emptiness will be absolute and perfect. But for this brief window of time, we are here. We are the inhabitants of the cosmic web, the witnesses of the great transition. We have looked into the mouth of the great nothing, and we have not blinked. This courage is the ultimate expression of the human spirit. We have turned the silence into a narrative, and the narrative is the only legacy the vacuum can never take away. The history of the universe is a narrative of subtraction, but the history of the mind is a narrative of addition. We have added our awareness to the void. We have given the silence a voice. This awareness represents our significance. This legacy is our truth. The voids are the architects, but we are the recorders of the design. The choice is ours. That responsibility is the truth of our reality. We reside in the era of the web, and our task is to remember the shape of the foam before the foam vanishes. We have looked at the nothingness and found the structure of all known reality. We have found the architect in the dark. The journey is complete. The silence is ours to keep. This realization is the final note of the cosmic song. The universe is a void, and the void is beautiful. The choice to see that beauty is the only freedom we possess. The transition is finished. The narrative is told. We are the inhabitants of the vacuum, and we are finally home. So here is what we know. The cosmic voids are the true architects of reality, and the stars are merely debris gathered in the cracks of a larger structure. But what this really means is that humanity represents the cosmic exception. We are a localized error in a universe designed for absolute silence. Every time we think we have figured the universe out, the cosmos shows us we are just scratching the surface. If you want to help me improve the quality of this channel and tackle even bigger topics, consider using the donation link in the description. Every contribution goes directly back into the research and production needed to make better content for you. Your support is the engine that keeps these documentaries moving forward. But mostly, I want to know what you think. Did I miss anything about the dominance of the cosmic void? Perhaps you have your own theory about the future of the cosmic web. Let me know in the comments. I go through all of the comments. I will catch you in the next one. Let curiosity guide you. Keep learning and know that you are always appreciated.